Hi, AP Chemistry time. Here I am with a bomb calorimetry question for you. And perhaps the first thing we might want to discuss is what is bomb calorimetry anyway? I have a picture of a bomb calorimeter down here, and you will see it, of course, right here, right? There's our bomb calorimeter. And let's just say what makes a bomb calorimeter so special? Well, you may remember our discussion about energy. And energy, which we denote as delta E, equals the combination of enthalpy, which is Q, plus work. Well, we could rewrite this and say, well, delta E equals Q plus work, which is P delta V. And delta V is our change in volume. Well, a bomb calorimeter has this portion to it, which is considered the bomb. Here I am. Yes, not only are some things the bomb, but this, in fact, is the bomb. Ha! Anyhow, this thing that is the bomb is constant volume. And since this thing won't change in volume, it won't allow anything to expand. If the volume's 0, the PV drops right out, and E will equal Q. And when E equals Q, delta E, in fact, equals delta H. All of the energy of the sample then is converted directly to heat, and it allows us to measure it. That's the whole thing with bomb calorimetry, is it's constant volume calorimetry. In other circumstances, that might not be perfectly true, and some of the energy will go into doing work, some kind of expansion, and then we don't get a true caloric value or a true heat value in joules. So that's what makes bomb calorimetry so darn special. And so now let's do a bomb calorimetry question, all right? And here we have a nutritionist determining the caloric intake or value of 10 grams of beef fat. And we have some information. Now, the thing about bomb calorimetry questions that makes it sometimes tricky is, I guess we have more information than we need. See, this bomb calorimeter, we put our sample in the bottom here, and when the sample's in the bomb, it's surrounded by water. And this water changes in temperature. And so here they are telling us the quantity of water that changes in temperature. They're saying it's, well, 2.5 kilograms. And at the end of the day, that doesn't matter for this question. So, I mean, we don't care how much water's in there because we have a change in temperature of that water, right? And we also have the heat capacity of the bomb calorimeter. So knowing those things, we in fact don't need the amount of water that's there, which is tricky, I know. But the big thing we always will need with bomb calorimetry is a change in temperature. And we have an initial and we have a final. We have 56.9 degrees Celsius. And we're going to subtract from that 25.0 degrees Celsius. And this is going to tell us our change in temperature. And our change in temperature will end up being 31.9 degrees. Now that's important, because we have this heat capacity up here, which is an invaluable piece of information about our bomb calorimeter. That heat capacity tells us information of how much heat is released per degree centigrade that the water rises. And so we take the quantity of temperature, which happens to be 31.9 degrees Celsius, and we multiply that by the heat capacity, which is 1.360 kilojoules per degree centigrade. And that cancels out our degrees centigrade. And we're, in fact, going to get the number of kilojoules, which is 43.38. And there is our answer, really. Let's pay attention to sig figs and say, look, we have 3 sig figs. So our answer, I suppose, is 43.4 kilojoules. And this temperature went up, so we can call this a negative value because it's exothermic. And so here we are. We found the number of joules. We did it in kilojoules. You could always write this as 43,400. If we wanted to put it in joules. And the question asks for joules, so let's be true to the question. The B part says 1 nutritional calorie is equal to 4184 joules. So what's the dietary caloric value of beef fat in terms of calories per gram? Well, we can take the quantity that we have there and convert that to calories, and then divide by grams. So let me just pull up an additional page here and say, look, from part A, we had 43,400 joules. And we're also being told that there are, what, 4184 joules per gram. Oops. So then we say 4184 joules. Oh, geez, wait a minute. Darn it. Well, hey, we all make mistakes, right? I want to flip that because I want to actually change to calories. And so in 1 calorie, it's 4184 joules. And the reason I had to flip that is I wanted my joules to cancel. Hey, learn from my mistakes. And that's going to allow me to end up getting calories. And that ends up getting me 10.37 calories. And then we want to know calories per gram is what it says. So if we're looking for calories per gram, I'm going to divide this by grams, in which we had 10 grams. And 10.37 divided by, well, 10 grams came out, or will come out, to just move the decimal one over, 1.037 calories per gram. And then I believe we have 3 sig figs, so it's 1.04 calories per gram. Now, the thing that makes bomb calorimetry so challenging is these pieces of information given are not always identical. But remember, when we look at this bomb calorimeter, that's the key. We want to take a look at our bomb calorimeter and make decisions from there. So we take a look at our bomb calorimeter and we say, look, the information we got this time was the capacity. And the capacity is huge. That's really important. You're always looking for the capacity of the bomb calorimeter. We're also always looking for a change in temperature of the bomb calorimeter. And in knowing both those things, we can get heat. And then we got to see where the information leads us, because not every question is identical. No one question requires any type of mathematical gymnastics that are too crazy, but they all somewhat are novel to one another, and that makes them challenging. So to look at this particular problem won't necessarily be exactly the same as every other, I guess is my point. And really look for the heat capacity, look for the change in temperature, and sort of feel your way out from there. Have a great day.